Alrighty, good afternoon everyone. We're going to go through the answers now to the revision test on Qlearn. This will all be available on our OneNote as well. Hopefully it's not going to be like our last recordings that we couldn't see where my mouse is, so hopefully we can see movements like that. Okay, let's get into it. Now, when you guys are doing this revision, I'm hoping that you haven't just learned how to memorize these multiple choice, but of course actually know how to do them, because in the exam it's very unlikely to be the exact same question. However, the skills that you learn will be very useful. Okay, the first one, the intensity of light at a distance r is measured as I. So we've got distance of r, we've got an intensity I. Okay, cool. I'm thinking about intensity. I know that the equation is, it's proportional to, I don't have my formula sheet in front of me, I forget the actual thing. Probably should grab that, but that's alright. It's proportional to 1 over r squared. If the distance is halved, okay, so if the distance is halved, what will happen to the intensity? Let's take a look. If I just do, just on my proportional relationship, that's that symbol there, 1 over 0.5 r, and that's all squared. What's going to happen is we're going to be doing 1 over 4 r squared. Okay, sorry, 0.5. Shouldn't do it like that. I'm going to rewrite it first, make a little bit more sense. It's going to be 1 over a half of r squared, which is 1 over 4 of r squared, which is equal to 4 over r squared, which is 4 of the intensity. So it's going to be 4i. Okay, same kind of question. Now this time it's going to be tripled. What will happen to the intensity? Well, we can already kind of just deduce that if the distance gets halved, the intensity gets brighter. That makes sense, right? You're getting closer to the source, it gets brighter. What's going to happen if you get further away? If the distance gets tripled, it's going to be 1/9 because of, again, that proportional relationship, that it's proportional to 1 over r squared. Okay, so if you put in 1 over 3r squared, that's going to be equal to 1 over 9r squared. And that's what we get 1/9. Okay, a current of 1 ampere flowing through a point of 1 second is defined as 1 coulomb. Okay, and you could go through a process of elimination, or you could just remember that definition. Okay, that ampere is measured in, or rather our current is measured in amps, but it's how many coulombs are going through at that point. Okay, we did a question very similar to this just the other day. 71 centimeter solenoid consists of 650 turns. Determine the magnitude of the magnetic field induced by a current of 3, and that actually should be 3 amps. So our current is equal to 3. Definitely should have brought my formula sheet with me, I'm realizing now. I might have to go grab that soon. But from memory, the magnetic field is equal to, we have a little n, we've got an L, and it must be I in the middle there. Okay, and you can swap them around as you need. Now to calculate little n, it's capital N divided by L. Capital N is the number of turns, so that's 650 divided by our length is 0.71, so I have to write that down, 0.71. And you can see that I've converted that to meters as well. It always has to be in meters. Now I can't do that in my head, unfortunately, so I'm just going to substitute it in directly. That n is equal to 650 over 0.71. That's my n, my little n, times by 0.71 times by my current of 3. Those two are actually going to cancel out. So 650 times by 3 is what, 1,800, 1,950? And Teslas for B. Okay, determine the direction. Now we can do our curl. If you don't remember the curl, you're going to have to look at your photos, your images that and notes that we've taken. But basically, if you've got a solenoid and it's got a whole bunch of turns, it's turning around this direction. All right, you can almost imagine wrapping your thumb around it, okay? And this is me trying to really badly, I'll try to do a different color. Your thumb wraps around, okay, sorry, other way around. Your fingers wrap around in that particular direction. So let's again try that again. Our fingers are going around this way, okay? And if we're holding it like this, all right, then your thumb is in that direction. However, if it's the other way around, that your fingers are curling around, Did I do this the wrong way? Fingers are curling around. Basically, we just have to look at the direction of our thumb. Now, in this case, our fingers, it's already getting told, it's coming around this way. We wrap our fingers around like this. So our fingers just come around the top, around the top, around the top, because our hand is here, which means our thumb is pointing out that way there. Okay, so it is pointing. And this one's the opposite. It's going around to the other direction, so it's going to be right. Okay, Snell's law problem. Particle of light passes through a couple of different mediums. The first is air, that's n equals 1. On an angle of incidence, I is equal to 32 degrees. It passes through a substance of refractive index 1.7 before passing through to another, which is 1.21, and then going back into the second one, which is n1.7. Okay, we are asked to calculate the refractive angle as it passes back into the second medium. So if we're taking a look here, we've got our angle of incidence at the top here, that's 32 degrees. We're going to find some angle of refraction in there, the angle of refraction. It's going to come down and become our, so let's say R1, that's our first refracted angle. Okay, and that refracts down and then refracts down one more time. So we need to do Snell's law once. This will be the second time, and the third time is going to give us our answer that we're looking for. So let's do it first. The first time we're doing Snell's law. N2 over N1, not the other way around. N2 over N1 equals sine of I over sine of R. And again, I didn't bring my calculator with me. I'm really realizing my rookie mistake here. So I might only do the first one and leave it for you guys to do a couple more. And if you need help, you can ask me in class. So N, as we go from 1 into 2, N2 is 1.7. N1 is coming from air, so it's 1. Our incident angle is 32 degrees. And we're looking to find the refracted angle. So let's rearrange this. 1.7 divided by 1, that's just 1.7. That's an easy one. R, chuck it over there, times it over there. 1.7 times by sine of R is equal to sine of 32 divided by 1.7 on both sides. And then we've got to get rid of sine, so sine to the inverse of sine 32 over 1.7. And that's going to give you the refracted angle 1. Okay, this one in here, refracted angle 1. And then that's going to become our new part, our new angle of incidence. So I is now equal to whatever this answer is. Okay, it's sine of inverse sine 32, 1.7. That's our new one. And now N1 is now 1.7, and our N2 is now 1.21. And I'll just say etc. And you'll have to do it a third time to get the answer. Okay, although that would be, I suppose, our law, that a current carrying conductor experiences a force and magnetic field. Okay, that's one of our laws. Okay, the motor effect refers to the left-hand rule. Okay, it's just a reference. It's one way that we can think about it. So that's a correction on that one, not the law, but the use of the word refer to. But that's a different part of circuitry. Okay, next one. An area is filled with a magnetic flux X, which has a density, flux density of B. Now, we sometimes refer to fluxes like this, and then also phi. Okay. Yep, perfect. So I'll do it in terms of the equation that I've given you. So magnetic flux equals BA. Okay. The magnetic flux has a flux density of B. Excellent. If the size of the area is doubled, okay, so the area is going to be doubled. A is going to become 2A. The new magnetic flux and the flux density is what? Now, I've given you a hint, and this is obviously super important. Obviously, number one, we have to remember that equation. The number two, magnetic flux is a constant. Okay, we've got two things, our flux and our flux density. Well, that's clearly there. Okay, and then our magnetic flux is X, and that's actually equal to BA. But the flux, magnetic flux, X, is a constant. So, if this number is staying the same, X is not changing, but the area has become 2 of the area, well, the way that this is going to be the same is of course by dividing by 2. That is the only way that that is going to stay the same. So therefore, if I'm looking at my options here, magnetic flux has been, where am I looking? Sorry, flux density. I'm looking at the second half. B on 2, so it's either one of these two, and the magnetic flux stays the same. It's a constant. So that's what happens there. Magnetic flux is a constant, so either way we could have actually just gotten rid of that option because it wasn't constant. It's not the same. And then we had to look at what was that B relationship. Did it double? Well, no, that would have become 4. All right, it didn't say the same because that would have been doubled if we halved it. It would say the same. Okay, the photoelectric effect. We remember that we've got some kind of light coming down normally on some kind of metal or something that can release electrons. Okay, and then those valence electrons get sent out. And I've just given you the key definition. It's the valence electrons are emitted. Now, technically, all of these are correct, but the photoelectric effect is all about the fact that those valence electrons are being emitted or they're being ejected. Okay, all of these do happen according to the kinetic particle theory model, but this is what the photoelectric effect is all about. Law of reflection. Okay, that means that your angle, I'll do it in terms of angles. The incident angle is equal to the angle of reflection. Easy one. When a wave is refracted, okay, the following properties are changed. What do we have? We can actually think about Snell's law for this. So n2 over n1 equals sine of I over sine of r. And we've got a couple of other things too. We've got lambda 2 over lambda 1. And we've also got v2 over v1. Okay, so taking a look at Snell's law, well, clearly the wavelength changes. So we've got that one or that one. And we've clearly got the velocity also changing. So, okay, again, only those two would be applicable, but the frequency does not change. Okay, so it's those two there. Okay, a mirror projects the following image qualities. If we think about, I'll put some kind of mirror. Okay, this is your real side, this is the virtual side. This is what's actually happening in the real world. Maybe you see yourself in front of the mirror. Yeah, there you are, and you're very happy to be in front of the mirror. Okay, this is you. There's not actually two types of you. Although you see yourself way over here, okay, this is not actually you. You're not in the wall. It's a virtual image. Okay, so it's either one of these three that are virtual. Cool. Now you see yourself the right way. Okay, so it's not the top one. So let's start eliminating. It's not that one. It's not that one. Both of these are upright, and it shouldn't be bigger or smaller. It should be the same size. That's the whole point of a mirror. So that is the following properties. What is the energy of a photon with a wavelength of 440 centimeters? Okay, and then submit your answer without the 10 to the negative 19 joules. Be very careful in the exam. Am I asking for joules or am I asking for electron volts? Remember, the way we convert is by doing 1.6 times 10 to the power of negative 19, because that's the charge of an electron. Okay, to find the energy though, you're going to use this equation, which is equal to hf. Okay, that's Planck's constant times by the frequency, but we can remember that the frequency is equal to lambda f, which means that it must be equal to v over lambda. Now, v for a electromagnetic wave is c, that's the speed of light. So that's equal to, oh, sorry, not e, what am I saying over here? It should be h. And h is equal to 6.626 times by 10 to the negative 34 from memory. C is equal to the speed of light, which is a constant of 3 times 10 to the 8, and lambda in our case is up here. It's 447 times by 10 to the negative 9. We have to convert that nanometers to meters times by 10 to the negative 9. All right, a couple of tricky ones. Transformer properties can be explained by what? The law of electromagnetic induction. Well, that's not right. It's not even a law. Is it the right-hand rule? No. Is it Faraday's law or is it Coulomb's law? It's Faraday's law. Coulomb's law describes, well, Coulomb actually has a couple of laws, but generally that refers to how kind of electrons move around the circuit in terms of generally its current or its charge. But in this case, it has nothing to do with transformers. What's the next one? What was one weakness of the relative model? Remember, there's two that are widely accepted. You have those two ones, weaknesses. Has to relate to its stability. That according to this, the electrons which orbit the positive nucleus should collapse inside. All right, it's very unstable. Those negative particles should just go straight in. The other one has to do with our spectra. Sorry, I'm getting knocks at the door. I think people just being annoying. We'll ignore them. Okay, and its inability to explain spectra. Spectra is the fact that if we look at any kind of atom or any kind of metal or a particle and its emission spectra, okay, sorry guys, just coming now. Yeah, if we shot like a laser at it, it's only able to accept different amounts of energy. That's what Bohr's model showed us, that like it's negative 13.6 or something eV, and then negative like 5 eV. Okay, and it's always the difference between them. And according to Rutherford's model, it could not explain those different wavelengths. Why is it that if we shot some light at a particle, it only would accept different kinds of energy amounts, not just a continuous amount? So in this terms, it could not explain spectral lines, but remember there is the other one as well. It definitely wasn't stable, incorrect. The electrons were negative, and it only accounted for particle nature. That's not quite right either. It did explain. Okay, this one here. For this one here, I misread one of my own pieces of writing. Okay, the correct option is obviously the bottom one. A photon transfers all of its energy to an electron only if it exceeds the threshold energy. Okay, so in this last one here, the key word is only. If we have some kind of photon from a light source, so I'll draw it over here. No, it's not the way of a torch, not a triangle. This way, shines in some light on a metal surface, and then electrons will get ejected. Okay, but for that light that's coming in, it is going to give all of that energy to those electrons to be emitted only if it exceeds the threshold energy. Okay, if it doesn't exceed it, then they're not going to be released. Okay, there's not enough energy to release them. They're very happy being stable in here. And if there's only just enough energy, well, they don't get released either. Okay, so only if it exceeds the threshold energy, all of its energy. Distinction of the last one. Okay, so, sorry. The velocity will decrease. Determine the energy release of an electron, moving from the third to the second. So it's going from here to here. And our delta energy is equal to EF minus EI. Make that a little smaller, that F. Okay, this is where we started, this is where we finish. So it's equal to negative 3.4 minus negative 1.151, which should be equal to, that's going to become a positive. So negative 3.4 plus 1.51, which is equal to negative 1.89. The direction of induced current is such that it opposes the change that it produced is whose law? Okay, this one here is Lenz's law. Okay, the whole idea that if you are creating a current because you're if you've got some kind of moving electron, sorry, other way around. You've got a moving magnet which creates an electric field. It's induced. It's going to be in the opposite direction of that that induced it. Okay, and we can remember the experiment when you drop that little marble through that tube. This guy right here is a magnet. It's moving. That's going to create an electric field. There's my electric field. It's moving out. Okay, but this guy right here, the other magnet, is going to be affected by that. Because now there's an electric field, that's going to make the magnet start moving. Okay, that's going to be moving in the opposite direction, hence slowing the magnet down. So it opposes it, and that is Lenz's law. The force of a charged particle moving in a magnetic field is given by what? All right, well, clearly we've got all these forces. That's just the most basic one. That's kinetic. That's actually centripetal motion. Year 11s will learn that next year. It's definitely between one of these. We've got a moving electric field. Well, if something is moving, it's got a velocity, so it must be this. Okay. By contrast, this is the force of two charged particles, Q and Q. Look at that. Two charged particles are separated by a distance of this. The first has a charge of this, while the second has a charge of this. What is the force between them? First things first, we want to convert that to just coulombs by remembering that mi goes to the -6. Okay, and what do you know? The equation's right there, the one that we need. So the force between it is equal to K. I think that's 9 times 10 to the -9 from memory. So hopefully we can do this without a book. I'll write the equation first. Let's go Q. over r squared from memory. So 9 times 10 to the negative 9 times by 5 times 10 to the negative 6. We don't care if they're positive or negative when we're determining the forces. We only look at the magnitude. And it's got a distance between them of 0.97 meters. It has to be converted. And we'll square that. And then that's whatever the answer is. Okay, two charged particles are separated by a distance of this. The first one is a charge of this, while the second is a charge of this. What is the electric field strength? Okay, we're finding something different now. We're finding E. Now, the only difference between this one and this equation is we only care about one of those charges. We aren't looking at the effect they have between the two. We only look at one of them. Okay, so what is the effect due to the first one at the point of the second? So we've got those two charges. They're both positive. This one is 8 microcoulombs, and this one is 1 microcoulomb. Okay, and this is radiating out some electric field. Okay, so it's going to be 9 times 10 to the negative 9. We're doing it due to the first, so it's 8 times 10 to the negative 6. And then it is 0.96 meters away. Squared. There's your answer. Okay, reflecting on the experiment where we investigated the refraction of light through a prism, two possible limitations were imperfections of the prism, absolutely. The table was unsteady. Yeah, maybe. And then inaccurately measuring the incident angle, definitely. Okay, all of these, of course, are true. However, just to be correct, I think those two are probably the most accurate. There's only 2 points, but truthfully though, if you argued this point, it wouldn't be wrong. But I want you to think more scientifically. Identify the following as either a step up, step down. Okay, we're going down in our turns, it's going to be a step down. All right, doing some experimental skills. Clearly we're going to need some kind of line of best fit. They haven't given us that. Well, we'll have to figure that out ourselves, I guess. Student investigated the effect of the velocity of an electron of a force. The effect of the velocity on the force. So V is equal to, is it QVB, I believe, from memory? And we are asked to find an experimental value for the magnetic field. We don't know it. We want to figure out what is B. Excellent. So let's take a look. I can see by comparing this to my linear relationship, y is equal to mx plus c. That's what we want it to look like. Now it's looking pretty similar. I can already deduce, therefore c is equal to 0. There's no y-intercept here. So y is equal to mx. I can see that my force is on the y-axis over here. That's my y, that's my x. So velocity is my x, so I'm going to move that to the side. So I'm going to go qbx, okay, because now it's looking a little bit more similar. But I'll write that as v, sorry. That was there, which means that m, the gradient, is equal to qb. Now we aren't told the charge of this particle. However, we are told that it's an electron. We know the charge of an electron. So therefore, m is equal to 1.6 times by 10 to the negative 19. Taking a look at our units, it's not in electron volts or anything like that, so it must be times 10 to the negative 19 times by b. So b is equal to m divided by 1.6 times by 10 to the negative 19. Unfortunately, we don't know m. We're going to have to figure it out. And we can do that by taking any pair of points and finding the difference between them, their gradient. Now, when you're doing this, I always recommend, first and foremost, look for points that might be going through corners. If you've got anything that goes through a corner, you're going to have a really good time. Unfortunately, it doesn't look like any of our data is going through a corner, so that kind of sucks, but that's okay, because the next thing you do is look for ones that are on the line, because at least you'll know exactly what it is. It's 80 in this case, or it's 60 here. If I take a look, this one is about exactly halfway, which is pretty sweet. And that's pretty close. So let's use those 2 points. M is equal to y2 minus y1 over x2 minus x1. My second y point is up here, or appears to be 1.1 times 10 to the negative 16 minus Definitely going to put that in brackets. That would be an 8 times by 10 to the negative 17. And then my x value would be about that middle point of 70 minus the x point of this one, which is about 50. Chuck that in the calculator. Can I do the difference between these? Well, that's clearly 20 on the bottom. Nah, that's a hard one to do, unfortunately. Can I factorize it? 1.1 times by 10 to the negative 16 minus 10 to the negative 16, so we'll minus that off. So we will be left with, nah, that's annoying. Oh well, chuck it in the calculator, find your m, and then divide those two numbers. I believe the answer was 10, I'm not too sure though. What do we got? A couple more questions. Let's get these last multiple choice ones out of the way. Electromagnetic waves made up of 2 what? Transverse longitudinal wave? Incorrect, absolutely not. You guys aren't looking at mechanical waves. Oscillating perpendicular waves, that's definitely true. All right, you've got the electromagnetic field, you've got electro and magnetism. They aren't parallel, they don't go in, so if I've got a particle going this way, you'll have maybe electricity going that way, and then the other one's going this way. They are 90 degrees. And they aren't mechanical waves, so it's that one. If the angle of incidence is 72 degrees, what is the angle of reflection? Well, it's 72 degrees, easy. A large refractive index will do what to light as it passes through its medium? Now you can think of any example, maybe going from air into water. We'll do, I definitely interpreted the question right. We'll do light as it, yep, so as it's going into a larger one. This one's 1.3, this one is 1. It's going to slow it down. Which law governs transformers? Now, if you do a quick Google, I do believe that Faraday's law comes up. Okay, I was actually expecting Lenz's law. However, both of them are kind of correct. Okay, both of them are kind of correct. The reason being is that Lenz's law is kind of the physics principle that started it all. Okay, the fact that if you can move some kind of magnet, right, you move it along, you've got a moving magnetic field, which means you're creating an electric field. Okay, and if that's around another piece of metal, for example, well then those electrons, that magnetic field is going to move those electrons, which means the magnetic field will move in the opposite direction. Okay, so for a transformer that's on each side, that was kind of the physics principle that I was going for that started it all. However, both of them are correct, so I will allow either, but I think I've coded it that that one is correct. Okay, last one, a bit of a hard one. Charged particle was released into a uniform magnetic field and created the following curved path. It has a velocity of 1.2 times by 10 to the 4 meters per second. It has a mass of 6 times by 10 to the negative 24 kilograms. So all of our units are good. The magnetic field strength, that's B, is 0.04 Tesla. Determine the charge of the particle. So what is Q equal to? And if you take a look, it's either plus or minus. So we're going to have to figure out, is it a positively charged particle or a negatively charged particle as well? Now for this question, we need to look at both the radius. We need the radius, sorry, which we can determine from the unit of measurement. So if we go from 0 all the way up to 4, well, that's clearly the diameter. Okay, so the diameter is equal to 4 millimeters, which means the radius must be 2 millimeters, right? But we must convert that as well to meters. So milliliters to the negative 3. So there we go there. Okay, now I have absolutely forgotten at the top of my head what that relationship is. Can I remember it from the top of my head? We've got these things here. Is it B is equal to just Q M R? No, it has a V in there. Q is equal to M Oh, hang on, I remember now. Now we've got force is equal to force. If we've got some kind of moving electric charge, okay, well that's going to create a force. And that's that equation that we had up above here. This one here, right? Yep, so QVB, because that that electrically charged particle is moving, it's going to create a force. It's going to want to curve either positively or negatively, depending on the particle. And you can use your left-hand rule for that. Hint, hint as to what the charge would be. Meanwhile, if it's moving in a circular motion, that's actually centripetal motion, which is equal to mv, is it over r squared or is it mv squared over r squared? I think I wrote it up here actually. I'm sure I did. I'm sure we saw it before. The different forces. No, I've gone past it. Come on. Ah, here we go. Yeah, it is. Oh, no, that's not right. mv squared over 2. No, that's not it. That's kinetic energy. Bother. I think it's that from memory. mv squared over r. Okay, so we've got our r, which is sweet. We've got the magnetic field. We've got the mass. We've got the velocity. Excellent. So let's start to rearrange it. We are asked to find the charge of the particle. So we're asked to find q. So I'm going to divide by v and b. You take a look, those v's are going to cancel. So it's m over r squared b. So q is equal to 6 times by 10 to the negative. That's definitely to the negative 4. Holy, that's a heavy particle. 6 times 10 to the 24 kilograms. Sure. Divide by r is 2 times 10 to the negative 3. Times by our magnetic field, which is 0.04. Chuck it in the calculator, and that's going to give you whatever the magnitude is between those. It's either 2.9 and 7.5, obviously. Okay. Now, for our direction here, we need to think about our left-hand rule. Okay, and Haley's given us that really nice acronym of FBI. What direction is your force? So you got your force is your thumb. I'll give it a bit of a curve. Whatever. The index finger is your magnetic field, your B, and then this way out here is your I. Okay, so one's going up and down, one's kind of going forwards and back, and the other one's going here. Okay, now looking at our diagram here, we can start to determine whether it's a positively or negatively charged particle. We're going to use our left-hand rule for that. So, the particle is clearly moving to the right. That means the current is left. So taking a look at our diagram, our current, right? The particle is moving this way, okay? So that means the current is to the left. So I will say the force is this way, or the velocity is this way, which means the current is that way, okay? That's to the left. We've got our index finger. I keep getting these wrong, sorry. That's your index finger going to the left. You've got your middle finger. Oh my god, I said it wrong again. My apologies, everyone. This is so hard to say. Middle finger to the left. Your pointer finger is going to the sky because it's coming out of the page, which means your thumb is pointing up. There it is there. Okay? This works for a negatively charged particle. And take a look. That's exactly what it did. It went up, which means it must be one of these, either one of those negative ones. And from memory, I think that it's actually negative 7.5c. Okay. However, if instead, again, this particle is moving this direction, that means the current's to the left, and this is out of the page, but if this dot went down, well, that's not what we were expecting, okay? Because this tells us that our thumb is pointing up. A negatively charged particle should be moving up in this situation. However, because it moved down, then it must be a positively charged particle, the opposite. So that's how we can kind of deduce that, using our left-hand rule. Okay, and hopefully that has made sense to everyone, and hopefully you don't need any more assistance with any more of these questions, but of course, you guys can ask me questions at any time. No worries at all. Have a good one, everyone. That's all good. That one was fine. That's all good. That's all good. That's all good. And then I missed the last question. Oh, did I miss that one too? I just didn't write the answer in because I don't have my calculator. That's okay. Yep, that one's fine. Didn't have a calculator. That's all good. That's all correct. That's all good. That's all good. And then I just missed this last one down here. But it's a good one to think about. Determine the direction of the electric field at a point X. So we know for electric charges, they go out kind of like this. Oh, they go out in all directions, actually. They go out there, out there, out there, out there, and out there. Now, if you've got a negative and a positive charge, it's pretty easy. You're going to have that negative to positive, and it goes out like so. Yep, and they just keep going in like that. Okay, they're attracted to each other. For these guys, we've got two positive charges. So they've got one going out here, this one's going out here, this one's going out here. However, at this point that they detect each other, they're not going to keep going in that direction, they're going to change directions, and they curve around. So a more accurate one would be this keeps going, that keeps going, that keeps going. But this one is going to start to curve down, and this one curves out here, this one will keep going down. But these ones will curl all the way around. And same with these ones, they will also curl out and down. They want nothing to do with each other, so these will curl. So at the point X, we can see that it's curling back in that direction, which means that one there must be the correct one. And those have all got an answer, unless I didn't have my calculator, and excellent. Okay, I hope that clarifies things.